Hello, welcome to the presentation on empirical models of the Poynting flux and their applications. This is part of the CEDAR 2020 Poynting Flux Grand Challenge Workshop. Revised models of the electric potentials and filament currents were created in 2005. These new models use spherical gap harmonic analysis to represent the electric and magnetic potentials. The magnetic potential is used to derive the field line current through the two-dimensional Laplacian operator. These potentials were first used in a field line current model in 2001. In 2005, it was realized that the FAC model could be used in combination with the electric potentials to obtain the Poynting flux or Joule heating. Of course, the electric field is obtained from the gradient of the electric potential, and the delta B is also obtained from the gradient of the magnetic potential, but rotated by 90 degrees. And here we see in the graph the northward component of the electric field and the eastward component of delta B. And Poynting flux is created from their cross product. In 2011, the paper is published that showed a very high correlation between the W5 heating rates and Champ and Grace neutral density measurements using the Jakia-Bowman 2008 model. Delta Tc is a parameter in the JB08 model that controls the global exospheric temperatures, and it can be predicted quite well using the W5 total Poynting flux and Joule heating using a differential equation that accounts for the cooling rates. It was found that the delta Tc parameter is more accurately modeled if the cooling rate varied in proportion to the Joule heating over the previous time period. This extra cooling was attributed to nitric oxide, and comparisons with SABRE measurements of nitric oxide emissions showed a very high correlation. A new model of exospheric temperatures has been developed that uses integrated Poynting flux. The first step in the development of this model is to derive the exospheric temperatures from measured densities using the NRL model with many years of data taken from the GRACE, CHAMP, and SWARM satellites. The second step is to use the positions of each measurement in latitude and solar local time to sort these data by location on a polyhedral grid. The next step is to fit all the data in each grid cell to an equation that represents the exospheric temperature in that cell. It is a function of several parameters. Several variations of the formulas were tested. The most accurate one is shown here that uses delta T from the Joule heating as well as solar indices and day of year and universal time. This is also repeated for each of the 1,620 grid cells. The next step is to use the fit results to evaluate the temperature in each grid cell for selected input conditions. If desired, triangular interpolation can be used to smooth the results within each cell. These four examples show the effects of increasing the delta T parameter. This is the temperature change due to overall heating that causes the locations of the peak exospheric temperature values to move from the low latitude dayside to the polar regions. In these examples, all other input parameters remain fixed. This graph shows results from the model in the time period of November of 2003 that had significant geomagnetic activity. Densities measured by the GRACE A satellite are shown in black on this graph. Original NRL density predictions are shown in blue, as well as predictions from the Jakia-Bowman 2008 model shown in green. The red line shows densities that are calculated from the new model that is abbreviated as exemplar, using the NRL model to get the densities from the exospheric temperatures that the model calculates. This graph shows the same time period in the same format, but using data from the CHAMP satellite rather than GRACE. Overall, it is seen that the exemplar model does better than the NRL model and JB08 models, in predicting the densities, especially where the densities reach their peak values. Meanwhile, new versions of the FAC and electric potential models have been under development. The FAC model by Edwards et al. Used data from Ørsted, Tramp, and Swarm satellites spanning several years. The sunward and dawn dust components of Delta-V were fit, rather than using magnetic potentials, and the FAC is computed directly from the curl. The new electric potential model, a provisional version at present, supplements the E2 data with electric fields from Swarm. This graph shows a comparison of Poynting flux calculated from the old and new models at 8 different orientations of the IMS clock angle. On the left shows the results calculated with the 2005 model. The right shows results from the new Edwards-Weimer models. The newer model shows higher level Poynting flux in the polar cap and near noon, particularly for positive and negative values of the Y component of the IMF. A motivating factor for the new models was for use in deriving the ionospheric height integrated conductivity values. An unexpected result was to show the differences between the Poynting flux and Joule heating as suggested by Art Richmond in 2010. Formulas presented by Aldo Am in 2001 are used, which were demonstrated by Green et al. In 2007. Here we show the formulas for calculating the Pedersen conductivity and the Hall conductivity using the horizontal component of the current and the electric fields. The neutral winds are ignored in these calculations, though the effects are thought to be small. In these calculations, the total horizontal current needs to be used. It is obtained from the sum of the divergence-free and curl-free components. The divergence-free part is typically associated with ionospheric Hall currents and needs to be obtained from an equivalent current function that is derived from ground-level magnetometer measurements. The spherical harmonic technique demonstrated in a 2019 paper is used. This was based on the work of Chapman and Bartels in 1940. The curl-free component is typically associated with ionospheric Pedersen currents that have a divergence that is closed by field-aligned currents, and it is obtained from the magnetic perturbations that are measured on satellites. The new FAC model is used to obtain the curl-free component of the ionospheric current. In this model, the FAC is calculated from the curl of the magnetic field, and where the magnetic field is modeled the spherical cap harmonics using data from the Ørsted, Champ, and Swarm satellites. The ionospheric current is simply proportional to the Delta-V rotated by 90 degrees. These maps show the data that are needed to get the conductivities. The left column shows the electric potential and the two components of the electric field. The middle column shows the equivalent current function that is calculated from ground-level magnetic fields and the two components of the divergence-free current that is calculated from this equivalent current. The right column shows the field-aligned current and the two components of the curl-free horizontal current that are proportional to the Delta-V rotated by 90 degrees. Here we have the Poynting flux that is calculated from the cross product of the electric and magnetic fields. Next to it is the Joule heating that is calculated from the dot product of the electric field with the total horizontal current using both the curl-free and divergent-free components. Comparing this with the Poynting flux, it is seen that energy is moved from the polar cap to the row zones. Below the Joule heating are the maps of the Pedersen and Hall conductivities that are derived. These maps show the expected enhancements of the values within the row zones. There are places where these derived conductivities may have unrealistic or negative values. The electric field tends to be very weak in these areas, causing greater uncertainty. And in places, the equivalent current functions do not exactly agree with the electric potentials. This page shows similar results with a change of the IMF clock angle to 90 degrees, whereas the previous page was for a clock angle of 180 degrees or southward. This is for plus Y orientation. Now on this page, the clock angle is changed to 270 degrees or a negative BY orientation. These maps show the differences between the Poynting flux and the geoheating. The dot product of the electric field with the curl-free component of the current is exactly equal to the Poynting flux, while the dot product of the electric field with the divergence-free component of the current produces all the differences between the geoheating and Poynting flux. So it is this dot product that is shown on these maps. The differences in the totals are always less than 1% of the total energy flux. On these maps you can see that the energy transfer is negative in the polar region to near noon and positive in the rho zones. Some final thoughts, some which may be controversial. One is that the empirical Poynting flux model does well for calculating the thermosphere temperature variations without the need for small-scale structure. Second, the electric fields in the ionosphere are known to have power spectra indicative of turbulence, in which energy cascades from large to small scales. The small-scale dissipation is proportional to the energy that flows in at large scales. Third, attempts to add small-scale electric field structure to numerical models will result in an overestimation of the geoheating, unless the conductivity values are known at the very same scales. The reason being that the conductivity is known to be anti-correlated with the electric field. When one goes up, the other goes down. Fourth, attempts to add small-scale structure to the electric field will result in an overestimation of the geoheating, unless the time duration or duty cycle of the fluctuations are known. A spike or jolt in an observed electric field may be present for only a small time after the satellite moves on, and it cannot be assumed that such spikes contribute to the energy flow for a long time period.